Welcome to the course Advanced Reaction Engineering. So, in this course we will discuss about polymaths and ordinary differential equation solver. So, how to solve ordinary differential equations by using polymaths. So, that we will discuss nonlinear regressions methods by using polymath, that we have discussed in our last class. So, today we will discuss about ordinary differential equations. So, in our means so far whatever you have discussed, so most of the cases whenever we are going to design a reactor, so means particularly packed bed reactors, so then there is a ordinary differential equations that coming in the design equations, or whenever going to design that reactor. So, with that reactors, that type of nonlinear ordinary differential equations, how to solve that using polymath software. So, that we will discuss. Here we have taken one example. So, here the oxidation reactions we have conducted ethylene to ethylene oxide. So, here ethylene is reactants, oxygen is the reactants, and product is ethylene oxides. So, A, B, that is the reactants, giving the C is the product. So, here volume changes is there. So, in this particular reactions, if we conduct these reactions in a packed bed reactors, so there we have to charge some catalyst also. Catalyst is required for this particular reaction. So, the catalyst is the solid catalyst. So, in the design purpose of the reactor, so how much quantity of the catalyst we need, we have to place inside of the reactors. So, that we have discussed. So, if this is the weight of the catalyst, so how much means let us say reactants A and B is passing through here and C we are getting. So, at a particular, if we put 10 kg of catalyst, we can get conversions, let us say 30% conversions we can get. So, if we put let us say 60 kg of catalyst, so then maybe x equals to 60% conversions we can get. So, as much as catalyst will increase, so it is linearly maybe the conversion changes like that way. So, once we have these reactors, so we have to decide or we have to design for this particular reactor. So, to get a desired conversion, so how much quantity of catalyst that we have to place inside of the reactor, that is the for the design purpose for this particular reactions. So, here pressure drop is also there in this packed bed reactors. So, pressure drop, if the reactions is taking place let us say 280 atm pressures, so there would be a pressure drop might be there. So, delta P would be there. So, how P by P naught equals to Y. So, this type of some equations we have derived in our earlier class. So, for by considering argon equations we have developed that. So, for this particular reactions, let us say these are the parameters are given. So, means molar flow rate of the reactants initial value. So, alpha value is given. So, alpha, that is the inverse of kg inverse or pound mass catalyst inverse, the units is the fractional volume change for this particular reactions. K prime is the reactions rate constant that is given. Okay. So, once we means design for these reactors for this particular reactions, so then the ordinary differential equation that usually comes on the times we did not solve, that means only just how to means what would be the means what are the design or differential equations coming and how to solve that we have not discussed, but just results we have discussed. Now, let us say this is the ordinary differential equation has come, that is the changes of conversions with respect to the catalyst weight. So, if we change catalyst weight, then conversions will change like this way, let us say this way W and X, this way you have discussed last time, and even pressure also Y, that is the P by P naught. So, that is the W. So, this also changes like this, means pressure drops will be there. So, that we have discussed, but now for this particular problem, so we will evaluate this by using this ordinary differential equations. For this particular examples, we have equation 1 and equation 2, these are the two ordinary differential equations we have in the left hand side, dy by dx by dw and dy by dw. So, by changes of the catalyst weights, pressures and conversion both will change, and in the right hand side of these equations we have conversions epsilon, that is the fractional volume changes that we know or we have evaluated, alpha value that is required. So, that is for here these equations and y equals to P by P naught, that is fractional pressures, changes of the pressures, and F A naught, that is the molar flow rates. So, that we have to use here in these equations, and K primes also you have to use in these equations. Okay. So, in these equations only in the right hand side is x and y that you have to put, y you have to get it from here, and that you have to substitute here by respective conversion, that is will changes, means how that is changes. And here fractional if be the ratio of the volumetric flow rate for isothermal conditions. So, V by V naught, V into V naught 1 plus E x by y, this type of equations or relationships we have discussed earlier. So, V by V naught, that equals to F, that is the factors or ratio of the volumetric flow rate at particular times, and initially what was fed. So, from the reactors entrance or inlet. So, here's y value is needed, and if E value is needed, E value is given here, y value we have to get it from here, conversions for a desired conversions, what would be that we can. Now, these two equations and these are the parameters we have to use in a Polymath software. So, now how to means use this, here's Polymath software, just we have to click on here, we have to, that would be opens, and then we have to go for differential equations by for solving. So, this type of window will appears, and then we have to go for programs. Once we go for programs, then DEQ equations, differential equations. So, differential equations we have to choose these buttons, and then or else we can use this shortcut button also, dx is given. So, it means differential equations solve, means this way also we can go, or by through programs also we can go. Then this type of here by clicking dx plus is there. So, this buttons you have to click, once it is clicks this type of window will appear. So, here d is given. So, dx by dw we can put it here, means the first differential equations put it here, and corresponding initial guess value you have to put it here. Okay. So, dx by dw, this was our equations, dx by dw equals to minus r a prime by f a naught. So, that we are doing putting dx dw minus r a prime by f a naught, and initial guess that you are putting 0. Okay. So, after that the screens will appear like this. Once we enter first differential equations and initial guess value, the window will appear like this. After that second differential equations we have, that also we have to put it here. So, dy by dw equals to this, we can put it here, and then initial guess, that is the y equals to P by P naught. So, its maximum value should be 1. So, therefore, initial guess is 1 we are putting, and after that you have to press done. Means second differential equations we have put here, first differential equation and corresponding initial guess value we have put it here, then the window will appear like this. Then we have to we can see that undefined variables. So, these are the parameters we have not put, means undefined variables in the differential equation, this window will appear by these cross lines, cross symbols. Okay. So, then we have to click on there, x equals to plus, these buttons you have to click. These are the called explicit equations, means the other parameter value we have to put. So, first r a minus r a primes, these equations we have put that corresponding value. So, we have to enter this r a primes minus r a primes, what is this? So, that value we have to, these equations we have to put, and after that respective parameters we have to put, means this epsilon value, f a naught value, alpha value, rate value, and k prime value. So, these are the parameters, means explicit equations you have to put. Once it is put, so then it would come or appear here. So, almost all parameters we have put it here. So, then we have to specify the initials and final value of the weight of the catalyst, means within what range we want to means study. So, initial value we have to put and then press OK. So, initial W equals to 0, means catalyst weight, means when we are taking the catalyst beds, W equals to 0 to W equals to let us say 60 kg, within that we want to study. If we want to do W equal to 70 kg. So, initial and final value you have to put, so based on that that would come. So, and the final value is 60 pound mass that we have taken, so that we are putting here, enter the limit value. Okay. So, then it would comes, or we have to press OK, and then see here's initial weight, final weight is given here, and initial conversions is 0, initial pressure ratio that is the given, that is once. So, that we have given. So, now it is, earlier it was cross. So, initial and final value of the independent variable difference not set. So, therefore, it is coming. So, now ready for solutions. So, all means parameters equations we have entered in the means for regressions or nonlinear ordinary differential equation solving. So, now ready for solutions. Then we have to choose is here RKF 45. So, that is methods of that solving methods. So, by default uses RKF 45 techniques. So, we will proceed for that. Okay. And then once RK 45, then we have to get the output. So, in the which forms we want to get output. So, that output in the form of reports, in the form of graphs, or in the form of tables, either 3 forms we can get. So, then we have to click on these. So, then all 3 forms we want to know. So, then press the print button. So, print buttons means that is indicated here. So, here that means to run these programs. Okay. So, once we click that, so then we will get in the form of reports. So, first we are getting the report. So, in the reports you can see initial this is the final value, means these are the 2 differential equations, these are the explicit equations, and these are the number of equations that was solved. So, through this the final value is coming here. So, now you can see in the form of tables, if you select the table. So, earlier here we have select also table also, first one is the report, then it is the table. So, F A naught value how it changes, alpha value how it changes, alpha value, and R A primes how it changes, red value how it changes with the changes of the catalyst. Catalyst weights we have taken 0 to up to 60 pound mass. So, that way it changes, Y how changes you can see in the form of tables, and x also changes, means when W equals to 0, x equal to 0. So, then gradually it is increasing. So, conversions. So, now if you want to in the form of graphs, so you will get W, this is changes W, this is x, and W with this is x and this is y. So, means conversion changes like this way and pressure changes like this way. Okay. So, pressure changes means pressure drop is there in the packed bed reactors. If we increase the weight of the catalyst inside of the reactors, though initially let us say it was here, let us say we have started the reactions with P equals to 20 bar, this is the reactions pressures, this is inlet. So, here pressure would be this is P0, this is P equals to let us say here maybe 10 bar. So, this is the difference due to the beds. If we further increase the catalyst weight up to this, it may be here pressure maybe 5 bars like that. So, 20 bars initially it was, from that it changes into that bar. So, y equals to P by P naught, P equals to or P naught equals to let us say 20 bars. So, P bar gradually decrease. So, this value y value would decrease. So, in these equations from these equations, if we solve these equations just by putting all parameters, there also you can see it is coming like that. But here's from this graph what the how much amount of the catalyst you have chosen or to get 60% conversion. So, here if we y this is the conversions or y axis is the conversions. So, here this is the 60%. So, if you draw lines from this and it is intersect with the green line. So, corresponding 48. So, 48 pound mass of the or kg of the catalyst we have to put to get the 60% conversions, and on that times what would be that pressures. So, that pressures may be here. So, that pressure drops at this particular catalyst at different locations you can get. So, inside of the bed, so what would be the respective pressures, means this is the y I said y equals to P by P naught. So, if P naught equals to let us say 20, if we multiply it with the y, that's corresponding, then P will count, P equals to 20 into P 0, 20 into Y equals to P. So, that way we can get respective pressures. So, this way we can solve this, means by using ordinary differential equations, means this would be the output in the form of graph or solutions. Okay. So, now or today we know means how to solve ordinary differential equation, just I am repeating this. So, if like this one differential equation, two differential equation is there, ordinary differential equations like that, if we have 2-3 different equations, ordinary differential equations, which with the use of Polymath ordinary differential equation solvers, if you want to use, or any others with MATLAB softwares, any other software also we can use to solve differential equations. Just I am showing here by using ODE how to means ordinary differential equation solver of Polymath, how we can solve ordinary differential equations. So, these are the differential equations we need, explicit equations, and this is the explicit equations also, these are the parameters we need. You have to put in this Polymath softwares one by ones, we have to put or we have to supply the initial guess value and within what range we can to solve this. So, the catalyst ranges, so that we have to place, and after that in the form of graph or in the form of tables or in the form of reports we can get, and here is the output value you can see, this is the output value or that in the form of reports you can see. So, this way means all parameters we can find out. So, the results we can get. Okay. So, we know how to solve a ordinary differential equations using Polymath software. So, thank you. So, today is up to this, and next day we will discuss something else. Thank you.